Didn't actually get into the scientific method. We just said we'd talk about it, right? Okay, so here we are. Scientific method. Okay? Learning something new is our ultimate goal. That's what we're trying to do with science. Okay? If we push that further, we're either learning something new so that we can tell the world that I have learned something new. Okay? And you might say that's a bit stupid, but we're saying I have learned something new to make you pay attention to me. Okay? So it's kind of egomaniacal. The other aspect from learning something new is that I could take that information and I can then spin it around and do something better with it. Okay? So we're always trying to somehow improve either just our knowledge base or what's actually out there and available. Okay? So it all starts with observation. Right? Everybody agree with that? You heard that before, scientific method, observation. Yeah, some head shakes, yeah, cool. What's the next step?
Question.
Okay. A question, and of course because scientists are egomaniacal, we don't want to use a word that everybody knows. We switch it to hypothesis. Okay. So we come up with an explanation for why that observation happens. This is one of the next big things that scientists do a little bit differently than nearly everybody else in the world, because we always make an observation, we make a hypothesis, and it usually stops there. Or we make that observation, and in the formation of our question, we now change it to not be a question, we change it to be a statement, and it's now a fact. Can't be a fact yet. What do we need to prove that it's a fact? We need a proof. We need an experiment to test that. Okay? So cool. That's kind of fun. Everybody, heads up, heads down. Each new word. Okay? So to that end, let's draw attention to something else. Admittedly, I screwed this up and just posted it. The lecture slides are available online. Writing word for word what comes down on the screen is probably an unnecessary task because it's already written down and provided for you. Just putting that out there. Okay? Experiment, right? So there we go. We design an experiment to test our hypothesis. Okay, we had a bunch of people say they've seen the scientific method. People did the reading for today? Yeah? So you all read in the textbook scientific method?
Yes.
Yes, you're all like, this is dumb. Oh, no, I wanted to jump in on that one. Okay, that's fine. That's fine. Let's just hold back on the yes. It's okay. So then what follows experiment then?
Analysis.
Is that what the textbook said?
Or no, it's like right after the experiment?
You all read it, right? What comes after the experiment? What's that?
Like a theory? Like those stuff?
Theory. Usually we end in a theory or
A law. Natural.
a law. And it's a nice, lovely, linear process. We go observation, hypothesis, experiment, ta-da, I'm awesome. And we look at all the science that gets published out in the world and we're like, wow, these people must be brilliant to have come up with these hypotheses that are exactly matched by their experimental data. That is phenomenally cool. And that's where it's a complete and utter lie. What is the next step? And Ethan, don't answer.
More experimentation.
Why would I do more experimentation?
Because not just getting your data from one experiment might not be the same if you did it again.
Okay, so repetition of an experiment is useful to make sure that the experiment was actually valid. Okay, why else might we do an experiment? Redo an experiment.
Your hypothesis was terrible.
Your hypothesis was terrible.
Accuracy.
The result of your experiment said,
Failed.
that was crap. I'm not going to publish that because that makes me look like an idiot. Okay? That's 99% of science. You utterly and miserably failed. Okay? You forgot to put the lid on the experiment and the animal ran away if you were doing experiments on animals. If you weren't doing experiments on animals, the animal probably shouldn't have run away because there shouldn't have been an animal. Right? Or the animal came in and stole your experiment. Okay? You have to readjust your hypothesis, readjust the experiment. And then what? Okay, we tried it again. Here's our experiment. Now what happens? You fail again. Okay. And again. and again. Okay? This is the level of insanity. We talked about scientists being egomaniacal. They're trying to make the world better. And it's not just that they're trying to make the world better, because people can do that. It's that they can make the world better. Okay? I have every confidence that somebody can make the world better. It ain't me. Okay? But somebody can do it. A scientist goes through and says, I can make the world better. That's a pretty bold statement to make. Right? And in that process, they screw up a bunch of times. Sometimes we see that failure when it's really catastrophic. I'm going to cure morning sickness so women, when they're pregnant, no longer have to be worried about like barfing their guts out. Fantastic. Here's this drug. Take this drug. Everybody can thank me later. 1959, what happened? Birth defects, because the drug actually was a mutagen and caused birth defects in all of the infants. And that becomes a problem. Okay? That now becomes a catastrophic failure that we then have to learn from. So one of the reasons why that one becomes so difficult is you can't really test drugs on humans without careful limitations. That's why it's hard to sometimes run experiments about these things. Okay? But we try to limit that so that when we move there, the failure isn't like death or mutations. Okay? Eventually, though, 1% of the time, probably less than that, we get lucky, and what happens? Success. And that success is where we move out into either a scientific theory or a natural law. We've expanded the knowledge. Again, wow. There's even a sound effect with it. Next time we move through the slides, listen. It's interesting. Right? We move into these two branches. Natural laws are kind of like the always true. Scientific theory, we don't really know yet. Okay? But we've got proof to suggest that that statement is true. Okay? And that becomes a hard one. There is proof behind a scientific theory. Okay? I have a theory that the sky will fall. What do you guys think? When I stepped outside yesterday, the sky was falling on me. It was rain. Okay? Is it always falling? No. Okay? And deciding what is the definition of the sky is falling. Okay? So we can come up with theories, but we have to have proof to support them. Without that proof, without the experiment, the hypothesis, and all the observation stuff to back it up, this isn't a theory. This is you just throwing crap at a wall and hoping it works. Okay? That's kind of like the... no, there was a word for it that escaped me, so I lost it. Okay? So, we need the experiment and the hypothesis to support our scientific theories. Okay? That's what gives them weight. Without the experiment and the hypothesis, we got nothing. We start with the observation. We don't start with the theory. Okay? So, chemistry's role in this big, huge, grand scheme of science. At one end of the bridge, we have mathematics and physics. At the other end of the bridge, you can tell how far into this I've gotten. You have biology and the other stuff that's out there. Okay? Chemistry is really bridging that gap. Okay? If we look at the kind of hierarchical nature behind science, it starts with mathematicians. Okay? You get mathematicians that get super cool and excited about playing with numbers and theories and letters and coming up with weird expressions that mean nothing. But it's cool that they do it. A physicist comes along and says, hey, that thing that you're playing with that generated some cool patterns actually explains gravity. That's what pisses off the mathematicians, because now their number junk means something. So they go back and they start playing with something else until a physicist comes back and says, hey, that stuff that you were playing with, that explains quantum mechanics. God, back to the drawing board. Okay? How many of you enjoyed a mathematics class? Yeah, not even half the class. Okay? That's a bit painful. Okay? Physicists try to make sense of that to apply it. Okay? But physicists are pretty well, and I don't really apologize. One of my good colleagues as a physicist, are pretty ingrained into the mathematics behind this. And so they're a little, like the mathematicians are way out there, like doing just bizarre stuff sometimes. Okay? My parents are mathematicians, it's okay. Physicists have a little bit of grounding in the real world, okay? But they're still a little too connected to the mathematicians. So we need somebody to connect the mathematics and the physicists to the biologists that are planted squarely in the real world saying, this is how things work. I can observe the patterns of how animals work or organs work, and this is why they work. Okay? That why comes all the way back to the physics and the mathematics. But the biologists don't understand the mathematics and the physics, okay? Which is understandable. They've got their head dealing with things that actually make sense that we can deal with. Okay? We can't be a jack of all trades. We need somebody to bridge that gap. Egomaniacal, right? We get the chemists sitting in the middle, taking the mathematics and trying to manipulate and organize them such that the biologists can use it and use that information to scaffold out to their larger observations. Okay? Every one of these pieces is important. So let me just be clear with that. I will rip on mathematicians, physicists, and biologists. Okay? But they are incredibly important. I'm not saying they aren't, just for the record. That said, chemists are more important. Thank you. Okay. Chemistry as a field, if we look at the general chemistry, so the first 3 semesters of chemistry are supposed to span everything. It's supposed to give you the fundamental basics of all chemistry, which is a bit daunting. It's so daunting that chemists actually broke down the field of chemistry into subdivisions. We get organic chemistry, which is the study of you might think organisms, it's really just the study of carbon. Okay? That's the primary focus. Because when we move to biochemistry, now we're looking at more the science of life. You're bringing in biology to it. What is the chemistry that supports biology directly? Does organic chemistry directly apply into that?
Kind of.
Absolutely, hands down, amazingly intricately tied. Does that mean a biochemist recognizes the other direction? No, and typically they don't, which is okay, but it's there. Inorganic chemistry. In mean not organic chemistry. Okay? Biochemistry has organic chemistry in it because it's not inorganic chemistry, not organic. It's not organic. Okay? Inorganic chemistry is now referring to not organic, so no carbon. Okay, primarily. So that's going to be focused a lot more with the metals and how they interact. Why do we have 2 separate fields, organic and inorganic?
Because organic is such a broad thing, it covers a lot of things.
Organic is a broad thing that covers carbon. You're going to tell me carbon is a broad thing in comparison to inorganic, which is everything else? Yeah, I know where you're going, but I don't quite buy it. Okay? The big reason why we get a differentiation here is the organic chemistry is focused primarily in carbon, very high up on the periodic table, and as we'll see later on, only has access to a few kind of reactive sites or reactivities. Inorganic chemistry primarily deals with this big section through the middle, a little bit lower on the periodic table. Guess what happens when we get a little bit lower on the periodic table? We get more reactive sites. Because we now have more reactive sites, the chemistry or the theories that we use to explain them have to develop beyond the limits of organic chemistry. Okay? Physical chemistry, those guys are really connected with the physicists. The physical is now, how do we explain ultimately the mathematics of all of those fields? Okay? So a physical chemist could look at every single one of those. Okay? So but physical are primarily focused in on the mathematics behind each of those. Kind of make sense? Okay. So, chapter 1, now done. So what we're going to do is skip PSS in chapter 2, because that's a bunch of math and numbers. And as you will probably find out, I don't really like math and numbers. Okay? So, chapter 3, we're going to jump up to a little bit on matter and what's going on with matter. Okay? So first and foremost, we want to address how we can look at matter. What are we looking at for our observation? Right, so there's two main classes of observation, qualitative and quantitative. What is the root of qualitative? Okay, qual, which sounds an awful lot like quality. Okay, quantitative, quantity like numbers. So if I wanted to reference the quality of my lunch, I might call or reference it how or describe it? Taste. Right? If I wanted to reference the quantity of my lunch, I might reference okay, how much, how many calories. Okay? So note we're bringing in a different descriptor of it. Okay? If I told you to tell me the taste of this apple, is it 10 or 1? 2. What the hell are you talking about? What do those numbers mean? Okay? Quality doesn't really have a numerical value associated with it. Okay? So, of course, we got a picture. What do you observe?
An animal.
The animal, obviously.
Okay? We have an animal. Qualitative or quantitative?
Quality.
Well, you can describe it as one, then it's like quality.
Ah. All we've done is identify the object. We haven't actually specified any qualitative or quantitative information about said object. If I change that statement to now be, there was one animal, we now have a quantitative observation. How do I make it qualitative?
Fluffy animal.
I don't know what it is with sheep and fluffy, but the other class suggested the same thing. A
Maybe like
fluffy
the wool, because some people do,
animal. What are you talking about the wool?
because it can close sometimes different fur. Let's say one the sheep is on a different land, one fur might be softer, one might be more like clumped together.
Okay, so you could be saying soft wool, okay, or for lack of a better descriptor, I'm going to go with clumpy wool. Okay, that would now be a qualitative observation of the wool that was present. I think you do another qualitative observation of the wool.
It's gray.
Okay, I'll accept gray. As we'll find, colors are very subjective.
Brown.
Okay, gray, brown. This becomes interesting. The qualitative observation, depending on the observer, does what? Changes. There's a slight flux within those qualitative observations. This is why when we make qualitative observations, we should be as accurate as possible and provide as much information as possible so that the next person knows what we're referencing. Okay? Can you bring in any other quantitative information?
You can do age, rears, one head.
Wait, there actually is.
It's not one animal. Whoops!
I just, yeah, I'm correct.
There's actually two animals in there. And if you look really closely, there's actually a bird back there. Again, people laughing, so that's a good sign. That was a joke. What else could you quantitate in here?
Big animal.
Is big
No.
quantifying?
Eyes. Ears.
Okay, we could go through the amount of eyes. Actually, it's not 2 eyes here. Would have got 3 eyes visible. So we could change that. I do like the idea of the size of the animal. Nobody has worked on a farm. Okay, it's weight. Anybody want to throw out a guess? If it makes you feel better, I have never worked on a farm. I have no idea how much that animal is going to weigh.
64 kilos.
64 kilos. We got some people being like, no, but I have no idea, so it's okay. Okay? Which of those observations is more important?
They're equal.
They're both equally important. Maybe. I am a butcher. Not like massacre person, but like I carve up animals to sell the meat. Do I care that the wool is fluffy?
No.
Is the qualitative observation any use to me?
What about the quality of
We could potentially switch it to now dropping in the quality of the meat, but we also can't observe that one officially quite yet either. Okay? So the butcher says qualitative observation at this stage useless. Okay? So that must mean the quantitative observation is the most important, and that's the one we have to key in on. I am now a sweater maker, because I don't have a better term for that. Okay. Taylor's kind of designing it, maybe. What's that?
I said designer.
A designer? Okay. Am I going to care about this being a 64-kilo animal that has 3 eyes?
No.
Okay. What am I going to care about?
The quality of the wool.
Is that soft, fluffy wool? Or is that clumpy, dirty, nasty stuff? Okay. So depending on the lens of our observer, we're going to get different results out of which one's more important to us. The same thing's going to happen with science. All of these observations are important. Okay? What we have to do is decide on our audience. Who are we selling this information to? Okay? And let's not be fooled. Scientists are selling information. How good are scientists at selling information? Good. Global warming, vaccines. Okay. Scientists are not the greatest at selling information. Okay. We make observations about the world around us and come up with theories, and then we try and sell those theories out to the world. Sometimes they're accepted well, sometimes they aren't. And a lot of that has to do with how we've packaged that information. So when we think about science, it's not just here's a fact and I'm happy with it. It's how do I then pitch that fact out to the rest of the world. Okay? Saw a hand?
Isn't there a way of quantitative to describe a lot of qualitative things?
So is there a way to quantitatively decide or describe qualitative observations? Yes, but by that same token, we could add qualitative to quantitative. Okay? And ultimately what happens is those qualitative things, it's kind of like grading. Okay? When we go through and grade in this class as a chemist, okay, when I go through and grade, what do I get to grade?
Quality of the work.
Quality of the work? The answer is if they're right or wrong. Okay? How do we decide if they're right or wrong? Based off of a quantitative observation. Most of what I do is very, I think the word is objective. I'm not the greatest with English, that's why I teach with an English partner to help me out with it. Okay? I think it's objective, it's black and white. It is this. Okay? This is why scientists suck at explaining things. Okay? Because, no, it's this. Well, what about this? No, it's this. That doesn't work as an argument. Okay? You have to have a little bit more background and feeling, per se, behind it. Okay? There's a lot of quantitative to it. Okay? How many of you in, say, your English essay writing class have it strictly qualitative? I mean, you receive points for your essays. Do you understand where every single one of those single points came from? Okay? I would argue you're going to have a hard time with that. It's one of the reasons why I've always had a hard time with English classes, okay, and writing in them. And in particular, as a scientist trying to get people to express science through writing, how do I grade that? Well, you talked about the ideas, but you didn't provide a decimal point here, -5. Why did I subtract 5 points? Okay, you got across the point behind it. The qualitative information is there. How do I now quantify that into a letter grade? That becomes challenging. Right? So we can invent systems to try to quantify qualitative observations, but ultimately those are a human invention of it, trying to come up with a numerical coding. And that is exceptionally challenging to come up with a coding that everybody can agree on. Okay? So why qualitative and quantitative? What is 70 to 80% of the composition of life? Water. Okay? And the biggest reason why we talk about this qualitative and quantitative stuff is that when we consider how science progressed, it's going to progress by making observations on the world around us. And we may be able to go through with that world around us, and we could see different things. What did we just walk through, other than just a weird sound effect? And I've got to be a little bit careful with the second one. Those of you wondering, what the heck is, stick your hand in front of your mouth and do.
There's like liquid, and there's also vapor, where you go breathe. Solid. Liquid.
Liquid.
Gas.
Yeah.
Wow.
We've got different phases of materials that are around us. Why is water such a special material? Not only is it everywhere, we get all of the phases. Okay? Most of our materials, or a lot of our materials, are not easy to get all three phases. Okay? So water's probably going to be our big driver behind making these observations of an attempt at solid, because it's snow, an attempt at liquid, because there's water down here, just ignore the mountains, okay? And an attempt at gas, because it's boiling out of the liquid. So you got to kind of ignore one phase in each case. Okay? So what could we observe about these? If I took the solid and I put it in my hand, what's the solid going to do?
It's going to stay put.
It's going to stay there. Okay? Just the solid. Don't bring temperature into it. So if we're looking at a solid, okay, the shape is constant. Okay? And again, we can always act on things to change it, but what we're saying is when I leave it there, it's constant. Okay? What happens with a liquid? Okay, so I take my hand, do the exact same thing, I put the liquid on my hand.
It's going to drip over.
It's going to drip all over. What does that mean about shape?
Not constant.
Okay, I like your word choice because I can spell both of those. Yeah, variables. Constant. Yeah, okay, I did get it. Okay, we could look at our shape being variable. There's a little bit of variation in there that we'll have to worry about, which we'll look at in a second. And what would happen if I tried to put that gas in my hand? Okay, I can't. Okay, that shape almost becomes non-existent, and it's not really non-existent. Existent. That's probably wrong, isn't it? Non-exist. We'll just say no. All right? Non-exist?
Non-existent.
There we go. Okay? Is the shape really non-existent? What is the shape? If I pour that or place that gas in my hand, what is the shape?
Like the tiny atoms that accumulate what it is. Like
You can't really see it.
Okay? What if I, had a nice little box up here? Okay, I put my hand in the box, sealed everything up so nothing could escape, and now I put the gas in my hand. What is the shape?
The shape of the box.
It's the shape of the box. When my hand's outside, what's the shape of the gas? The shape of the room. It's the shape of the container that it's in. Okay? So it's not so much that it's non-existent, it's based on the container. Okay? When we go back and look at the liquid, okay, we said the shape was not constant. Well, the gas was also not constant as well. Okay? The shape of our liquid is a little bit variable, because when I pour it in my hand, it does move. What's it going to do? Move to match the volume of the container that's holding it. Okay? So the palm of my hand has a very small volume. The excess spills over the edges. Okay? And it's now taking up whatever volume it can within the rest of the container. Okay? So the container has some aspect to it, but it's going to be dependent on the volume, which gets us to, beyond shape, volume. What would the volume of the gas be? The volume is variable and dependent on, well, there it is, dependent on the container that holds it. What about the volume of the liquid? Okay. The volume of the liquid isn't variable, because then if I poured out the liquid and we had that liquid there, if it's variable,
It stays in that.
it could move and change all directions. It's not really changing, it's displacing where that volume is located. The volume is still constant. And for our solid, well, if the shape was constant, your volume ends up being constant. Which gets into the next kind of application of these, which we'll hold off on that term and go to describe these things. So I'm going to pick a particle. That particle is going to look like a circle. Ta-da! Okay. If it was a solid, would I expect a single particle? No. I'd probably expect a whole bunch of particles, right? Because if I take this table, a solid, I could cut it in half. I still have particles, right? And I could continue to cut it in half, and I still have particles. They're still all solids. So if I want to add another particle to represent the solid, where does that other particle go?
Right next to it.
Right next to it. And the next one?
Right next to it.
Yeah? Those are all supposed to be the exact same size circle, by the way, because they're all the same particle. Okay? Does that image match with our shape and volume? Okay. For the shape, it has to be constant. Could I move those around and really change much of the shape? They're all right next to each other. They all have to stay right next to each other, otherwise they're not a solid. That helps to explain our shape being constant. Volume being constant. Each of those spheres is taking up a volume. The only remaining leftover volume is the tiny little white space. That tiny little white space is so small that I can't really change the volume of the solid. What happens when I move to a liquid?
They can be slightly more apart
Right? They're going to be slightly more apart. Why would they be slightly more apart?
because they have a variable shape.
Because the shape is variable. They have to be able to shift around a little bit. Okay? The volume is also supposed to be constant, which means the white space in between is still relatively tiny. Okay? And we run into that term relatively kind of a lot. You like that? We run into relatively kind of a lot. Okay? But that's our case. What happens when we move to the gas?
The space between the particles is
Now the space between those particles is relatively huge. Okay? That explains why our shape fills the container, because they are so far away from each other, they're trying to push on the walls of the container. Okay? Why the volume is variable, as I change the shape of the container, remember the gas particles are trying to get away from each other as much as possible. Our volume is going to change. What happens with the liquid? The shape's not constant, so these particles can slide around, but they still kind of have to stay in contact. The volume is constant. Okay? The particles, the white space in between, relatively small in comparison to the size of the particles. Okay? Solid, same deal, except more extreme. So the last big one that we could throw in here, because the textbook likes to throw it in there, compressibility. What do you think for the solid? Should it be compressible? No. Why not? What does it mean to compress?
pushed together.
We push together. How much more together can I make the solid? I can't, which means the compressibility is non-existent. That's another existent word. So let's just go with not. Okay? What happens with the liquid? Well, again, my picture's not the greatest. We get a little bit, but again, not a lot. Remember that white space is relatively tiny. Okay? So with our compression, again, pretty much not. So we'll even do a little squiggly not. It's about not compressible. And with our gases, yeah, we've got so much white space that I can shrink the distance between those significantly. So I can get a significant amount of compressibility.
Not.
Or a lot. But I like not. Kind of make sense? So again, we're just making observations on the world around us, allowing us to draw conclusions about what we expect these tiny little particles to be and how we expect them to act, okay? Based off of relatively simple observations. Cool? Okay, so there's all the text. So we take these three phases of matter, or three phases, and we now apply them to matter and say everything is made up of these three phases. How do we organize them a little bit further? Okay, so we encounter two primary categories. We end up with mixtures, which are now spatially linked, and pure substances, which are chemically linked. What was the name of this class? Chemistry. And on the second day of class, we are using the word, effectively chemistry, to define a different substance, right? To define pure substance. The reason we call it a chemistry class is because what are you supposed to learn by the end of the class? Chemistry. Well, thankfully, this isn't officially the first chemistry class. A couple people sent some emails in. Is this your first chemistry class? There are a significant amount of yeses in the room. We are using the word chemistry to define a different word that we haven't initially defined to begin with. That's kind of cyclic logic. We've got some problems with that. Okay? So be aware that we will encounter cases like that. You almost kind of have to take it as truth until you can understand a little bit more about it. Okay? So let's pick the easier one. Let's pick mixtures spatially linked. Okay, so these are not chemically connected things. Okay, so they're just near each other. Mixtures divide out into two categories: heterogeneous and homogeneous. Right? Hetero relationships, male-female. Homo relationships, male-male, female-female. Right? In the case of those relationships, we're referencing the sex, the biological sex of those partners. What would we be referencing in the mixtures?
The separation.
Separation is an action. Sex is a noun. What are we referencing? What's the same, what's not the same? What's the thing?
Your body
We may have just discussed it. And if you want, we can even throw in an S there. Element and solids were both wrong. You all have played this game before, right? You just work on just throwing answers out. You also might be a little hesitant to just shout out answers on that because I may have provided the wrong number of lines. What did you say? A? Yeah? Shape's not a bad guess. It's also wrong, but
Fingers and toes, or how much we would.
hopefully I don't get that far. We literally just talked about it. Somebody over there just mumbled it out. Not states. There's a lot of words that have that many letters that would kind of work here. So maybe you're like, well, the S, well, you said states, so clearly that didn't matter, so we can help out. I spelled it right, by the way. Star Trek? Star Trek, what do they use? They don't use face. Yeah. There was a hint.
Someone said it over there.
Yeah, that's why I pointed and no one fished it out louder. I needed to hear it louder. Phases. Okay, what we're referencing is the separation here is looking at the phases. So if I have a heterogeneous system, what am I looking at as far as phases?
Different phases.
I'm looking at different phases. Okay? So this would be 2 plus phases. If I have a homogeneous,
Well, one phase.
One phase. Okay? So, let's throw it out there. Let's start with an example. Give me the phase for oil. Liquid. Good. Give me the phase for water. Liquid. How many phases do we have here? By mixed oil and water.
Two.
Why two? Didn't you both say they were liquids?
Oh, because they don't mix in together. They're visible.
Right? And so the mixing part becomes an interesting challenge. We say, oh, wait, they don't mix. If I put oil on top of water, by definition, that is a mixture, right? Because they're in the same container. So what you're saying is that when I do that and make that mixture, what happens? There's separation. So the mixture of oil and water is heterogeneous. There are two phases, even though they're both liquids. Those two phases don't interact with each other. Okay? What else would be an example of a heterogeneous mixture? Salt and water is a good idea. Let's go ahead and a pizza. Damn. Okay, a pizza. Why is a pizza heterogeneous?
Yeah, it's cheese and sauce.
We can see the physical separation between each of those pieces. Maybe after we ate said pizza, maybe we wouldn't be able to see those separation anymore. Okay, but I would argue that's still dealing with solids and solids. How about two different phases? And so what I think is happening here is a lot of people are like, that's not a mixture. Salad dressing, I'll go with oil and vinegar. Salad, I'll put in the pizza category. What did you say?
Ice and water.
Ice and water is actually a challenging one for me to line up here, so I'm going to dodge that and say I don't want that one. But I like the idea. I'm going to switch it instead of saying ice, I'm going to say sand and water. What happens when I take sand and add it to water?
It makes it horrible drink.
Well, I see a physical separation. Why is there a physical separation? Because sand doesn't dissolve in water. Okay, so they don't mix. I see two phases. Yes?
There was, I think the example the book used was if you were panning for gold, like the gold and the rocks, not the minerals, how they separate.
Yep. So you could use gold in comparison to rocks when sifting through water. It's the same idea. You're taking advantage of how those multiple phases don't interact with each other. You can then see those multiple phases. Make sense? Okay. A suggestion was thrown out for salt and water. I carefully delayed where I placed that. What happens when I add solid salt to liquid water? It dissolves to make how many phases? One phase. There's only one visible phase. That's going to be a homogeneous system. What is the name of that phase? Salt water is the name of the substance, not the name of the phase, but good guess. Liquid. The phases apply to pure substances. Is salt water a pure substance? Where is salt water showing up? Under a mixture. So by definition, it's not a pure substance. So we cannot call it a liquid. Well, then it must be a solid. No, that didn't work either. So I guess it's a gas? No. What phase is it? Homogeneous mixture is a nice dodge on that. There's actually a fourth phase that we could use to represent a homogeneous mixture, and in particular, a homogeneous mixture in water. Why would I invent a new phase for a homogeneous mixture with water? Water is 70-80% of what we work with. Because water is so ubiquitous and common, I'm going to invent a phase to describe what it means to be dissolved in water. The name of that phase? Solution does not begin with A. It's a good one. Aqueous, aqueous, aquafina, fine water. Aqueous, dissolved in water. All right? Are there other liquids that we could dissolve things in?
Yeah.
Yes. Do they have a new phase name? No. Why not? Water is 70–80% of what we deal with. Okay? Because water is so common, we invent a new phase to describe those mixtures. The other ones do exist. We don't call them by any special names. Kind of make sense?
Do you just, like, what do you call it, just by their parts?
You would call it a solution. You could even call it a homogeneous solution. Okay? What do you guys think? You got it? So some people were even confident enough to say no. Good. Because of course, what am I going to do? What is fog?
Water vapor.
Is that a heterogeneous or is that a homogeneous mixture? By definition, it's going to be a mixture because what is in fog? Water and air. So now the question is, homogeneous or heterogeneous? Why homogeneous? There's no visible separation, so you were describing fog as a combination of a single phase being gases. What is in this room right now?
Air.
Air, which is a mixture of gases. Can you see me? Okay, just checking. If the room was filled with fog, let's I know we don't see it very often, but like huge, massive amounts of fog. If you've been in an airplane and you're looking across and you're like, whoa, where did everything go? Like the clouds, that's fog. Would you be able to see me?
No.
Why not? You just said fog was just a mixture of air. Well, what's in here is a mixture of air. Why can't you see me if I put fog in here? There has to be something that is causing the light to not pass straight through. Light passes through air. What is hitting the light, causing it to not pass straight through? Liquid. Fog is a mixture of two phases. Liquid water and gaseous air. Fog is a heterogeneous mixture. We have two different phases. And for those of you saying, but that's not visible, also take a look at what is visible next to the word visible. Primarily on both the left and right hand side of it. Quotations, meaning like, Mike is not a jerk. Okay. Quotations tend to imply some potential trickiness. When we think about heterogeneous and homogeneous, almost universally, what are we referencing? It's either one or the other. It's either black or it's white. Anybody seen a black and white movie? Okay, so a lot of head shakes, or at least seen something that's like black and white film, right? So there's no other colors in that except black and white. There's gray. What we're looking at is a spectrum of things. At one end of that spectrum, we are heterogeneous. At the other end of that spectrum, we are homogeneous. There's a bunch of gray areas in between. I want you to be aware that this is not black and white. We have gray areas. You have to be thinking about those gray areas, like our fog. We will encounter multiple sections or multiple concepts that are presented as black and white. Nearly everything in chemistry has a gray area. We've just established a line to cut it off. Okay? So, primary differences, two-phase versus one-phase, which might also elicit another question. What are the odds that I would ask a test question on the gray area? Oh, see? Some people took the air quotes to mean literally, Mike is a jerk. Okay? No, I don't test on the gray area. Okay? We talk about the gray area, I test on the black and white. Okay? Which gets us to the next section, as my foot starts hurting. Pure substance is now chemically linked. Okay? The pure substance breaks down into two separate categories, compounds and elements. So we look at the smallest individual particle, and we call that an element. Okay? Because our particles for our elements are so insanely tiny, if I was going to say, reference any one of them, I'm talking about a whole bunch of that same particle being there. Okay? So if I'm looking at, say, a sample of gold, I'm going to reference it as an element. It is one type of element, but there could be billions of particles there. Okay? If I now switch to a compound, what makes the compound different than the element? Two or more elements that are present. Okay? So let's take a look at an example here. What do we have? Okay. For those of you going, you just drew an O and a Z. Apologize for my unclearness. That's an O and a 2. A couple other people were throwing some other words out that weren't just O and 2. What were you throwing out? Oxygen. How did you know it was oxygen?
Is it a symbol of oxygen right there?
You knew, based off of past experiences, that our elements have symbols, and instead of referencing them only by the symbol, we could also reference them by the name. For instance, I'm not Mike McFablin, I'm Michael McFablin, and yet you call me Mike. Okay? We use shorthands. There's a shorthand. Oxygen happens to be a particularly special element, and that when we look at oxygen as an element, it shows up with 2 of them. So the 2 is there to reference the amount of oxygen. Okay? Would this be an element or a compound? It's an element, okay? Because there is only one type, oxygen. It doesn't matter that I have 2 of them there. There's only one type. So far, so good? What do I have now? I have water. Element or compound? Compound. How do you know that? Okay. We have hydrogen as a different symbol than our oxygen. So we have at least 2 different elements. Don't even really care about the numbers, but let's go ahead and deal with it. That 2 means what?
2 hydrogens.
2 hydrogens. How did you know that? Because I didn't tell you that. Okay. Our past experiences, there's a notation, a language associated with chemistry, some of which you've picked up already. Okay? Putting a number in the lower right-hand corner specifies the amount of the thing in front of it. Okay? And in this position, the amount of those atoms. Okay? And for those of you going, well, that's simple and dumb, I knew that already. At least twice in this semester, you will screw that up. Royally. Yeah. Okay, I heard the what. Okay, you will. It's okay. We have to remember that meaning. It'll come back and haunt us. Okay? So we ready for the next thing? I want to make water. What do I need to make it?
2 hydrogen atoms and an oxygen atom.
I would need oxygen, conveniently already drawn, and hydrogen. Okay? If I was going to say make it, I could add an arrow here to say I start with these and it makes this. Okay, for those of you trying to balance, be like numbers don't match, this isn't math yet, don't worry about it. We have H, we have O, ta-da, there it is. What do I have in the black box? Compound or element?
Compound.
What do I have in the red box?
Element.
Okay, I heard everybody say element, so there is only one type. In this red box, I have O and I have O. That's not O. Also a compound? What did I say I was mixing? Hydrogen and oxygen. What would allow me to suggest that I am not drawing that as a compound? Because a compound is chemically linked. When I said I made water, I'm taking hydrogen, hydrogen with oxygen, going through something to make water. We didn't even drop phases into it. We could still make the water the same phase to kind of break you on that one. Sorry.
Before the reaction hasn't really taken place, so if
Right now it's just.
What about that information would allow you to see that? So maybe what helps here is what is the red box? That is a possible conclusion from that, but I would argue no, because what did I say happened here? What did I mix? Hydrogen and oxygen to make water. I did not say I mixed hydrogen peroxide to make water.
You need a plus on the hydrogen.
I don't need that, but you're getting at the right idea. What is in the red box? Tell me what that red box is. To help you out, the answer is on the screen. And as a hint, it is not compound. It's not element. If it was a pure substance, then it would have to be classified as one of those two, so it can't be a pure substance.
Physical separation.
So we could jump straight to matter, and I'm going to say, yes, you're right, it is matter, but you can do better. It's a mixture. These two substances are spatially linked, not chemically linked. If I added in the phase information, which I didn't, we could further differentiate and say that this mixture was actually a homogeneous mixture. Okay? So we're taking a mixture and somehow that is becoming a substance. What about how that is written clues you that the black box should be a compound or a substance and the red box should be a mixture?
They're far apart.
Literally, the distance between those symbols tells us information about whether it's a compound, or sorry, a substance or a mixture. How much is enough space?
A space.
5 pixels. If it is 4 pixels, it is considered a compound, a pure substance. If it is 5 or more pixels, it is now a mixture. That would be a lie. That's not true. Okay? It's really kind of hard to tell with a space, right? You can't really tell. Is that a double space? Is that 5 pixels? That's a lot more than 5 pixels. Okay? How would we help clarify our language so that when I look at that, I know it is a mixture? Someone said it over there. What can I put in between these two symbols? A plus. Again, this is one of those incredibly duh statements. Okay? As an incredibly duh statement, now that we've seen the answer, how long did it take you to get to that? It wasn't incredibly obvious. Okay? You have to think about some of the history behind the language that we're using. If you know the language, you can help to apply that knowledge better. That's why we spent gloriously painful amount of time talking about that. I also think it's kind of neat. Just a little bit of space, and all of a sudden we change the meaning. Make sense? Okay. I even hear a thank you, dude. And not in a nice thank you. The next part, when we look at our elements, okay, because we got our periodic table of elements, is we want to think about how that periodic table is classified. Okay? There is tons of organization behind it, and in fact, there are millions of answers in the periodic table. Right? The question is, how do you pull that information out? The first one to deal with is metals versus nonmetals. Okay, these were the two big classes. Why might we have separated out metals and nonmetals for classes? They behave differently. Reacts with nonmetals. Reacts with everything. That's a pretty big difference. Low melting points. High melting points. So by looking at these classes, we can now group and categorize these things according to their properties. That's pretty cool. Right? When we look at those properties, how many of you would be able to, if I told you silver, tell me what all the properties were?
Shiny.
Why are you saying it's shiny?
Reflects the light.
How do you know that? Because I said silver.
I just know silver.
Ah, you have a past experience with silver. Okay, so maybe that's not fair. Osmium. I don't have any past experience with that. Exactly right. Okay. What we would hope is that we could organize our periodic table to help hint at some of those traits so that I don't have to piecemeal everything out. Okay? Some of our periodic table is organized such that almost all of them are metals. And the other part of the periodic table is now nonmetals. Does anybody see any kind of dividing, say, staircases in our periodic table? Yeah. What is that staircase dividing? The metals and nonmetals. The metals are all found to the left of that staircase. Osmium is kind of dead in the middle, 76. OS. Can you tell me something about its properties now? It's a metal. That's not a proper, sort of a property. Give me more. It's malleable. It conducts electricity. Okay? It has a high melting point. Okay? So that simple classification allows me to get through a lot of physical properties, which is kind of cool. So the periodic table has that built in. What if we look at, say, silicon? Si. Where is silicon?
To the right.
On the staircase. Right? It is officially to the right of the staircase, so we might classify it as non-metal. But it's on the staircase, and then we got aluminum right here. Immediately next to it, and you're going to say across that line is this infinite divide where all of a sudden we become metal, and then on the other side we're non-metal? Doesn't quite work that way. That staircase, we get kind of a gray area. Oh God, gray areas? Yes. In that gray area, we have a crossover between both the metals and the nonmetals. That gray area means you could be shiny, but you could also be brittle. Okay? It picks up properties across both. Okay? Which makes them infinitely more difficult to predict based off of those physical properties. Okay? So you will never see me ask a question, is silicon a metal or a nonmetal or a metalloid? Okay? Because that sits right on the staircase. Right? That's too hard to pick out. But what I could do is say silicon has the properties of being a solid. It is dull, but it conducts electricity, and it has a low density. What kind of metal is it? Or metal, nonmetal, metalloid? Okay. Now, by knowing what those properties are and knowing that we have a mix of both, you would know it's a metalloid. Does that make sense? You have to apply the knowledge, not just memorize what's on the board. Okay. That said, could you also just memorize what's on the board? Yeah. Okay. You have to be a little bit careful with that because the staircase isn't perfect. Some are nonmetals, some are metals, some are metalloids, depending on where they are on that staircase. If you use your textbook, it color codes them differently. Our lab or our periodic table doesn't do that. We got pretty pictures, so they're pretty pictures. We're just going to skip that. We'll jump right to our lovely periodic table. Right at the top, we have a big old piece of useful information there. Canvas, files, references, and then it says elements for memory. Okay, we've already talked about some of these. O was oxygen, H was hydrogen, OS was osmium. Okay? How do we know those? How do we know that those letters match to that element?
Memorize it.
We memorized it. How else would you know it? Shaking your head's a good answer. I like that. You don't. There's only one way to know it. You memorized it. Okay? So you are expected to memorize the language of the periodic table. You need to know that those symbols mean different names. Okay? So that's our first memorization task. How many of you want to memorize all 118? I don't like that question. Let's switch that around. How many of you don't want to memorize? Yeah, I think that's what I want. Don't want to memorize 118. Okay, so only the people raising their hands don't have to memorize all 118. Everybody else needs to. And for those of you going, you didn't take a picture, there's a camera right there. Okay? Welcome to the fun of our next exam. Okay? That doesn't mean I have to write 2 tests. That's going to kind of suck. So for those of you that said you didn't want to memorize all 118, there's that file, Elements for Memory. Go ahead and open it up. It's a pretty cool, useful file, because what it does is it lists all of the elements by name, and the elements it's listing are not 118. It's like 60. So it's not that much, but half, right? Half of an improvement. Those 60 you should commit to memory. This file was not created by me. It was created by colleagues that taught general chemistry, right? Because I don't like general chemistry. I kind of ignore it and don't worry about it. But they went through and said, these need to be memorized because we use them. I have a horrible memory, so I went through and said, I'm not going to use that. I'm not going to use that. I'm not going to use that. So I dropped it down to probably something like 40, okay, that you should memorize. How would you see that difference in the file? Bolding. If they're bolded words, you should commit that to memory. If they're not bolded, probably not worth memorizing. Okay? So spend some time this weekend working on that. Yeah, I will test you on that.